Well, is going to speak about modeling atomic impurities in nickelates.
First of all, I want to thank organizers for this wonderful workshop and giving me the opportunity to share my work. Also, before proceeding, I want to thank Gertrude Zechnigal for very fruitful discussion on this topic. So I am PhD student at the University of Bordeaux, working at a lab called LOMA under the supervision of Claudine Lacroix and Sebastian Burden. And today I am going to discuss about my ongoing PhD work on modeling atomic impurities in nickelates. Okay, so when we look at the history of superconductivity, we find that in late 20th century, there are many cuprate compounds has been discovered, which shows the superconductivity and which are layered. And nickel, being the neighbor of copper, is expected to show the same superconductivity. But it was predicted also in that tenure of time, but it takes around 30 years to synthesize that. And recently, in 2019, Harold Hwang groups at Stanford University able to synthesize this layered nickelates and show that there is superconductivity exists in this. So we will be looking the effective microscopic models for nickelates, and in part 1, and in part 2 we will be looking at the role of impurities in this nickelates. So is the first question we can ask to ourselves that nickelates are really the cuprate analogs? So there are certain similarities, of course, but there are subtle differences. Similarities as of they both are the layered structure. They both have high TCs, and 3D x square minus y square orbital is dominating in both cuprates and nickelates. And they both are doping induced superconductors. But what are the subtle differences? The subtle differences here are if you look at a phase diagram, the nickelates is weakly insulating in high and low doping, while as metallic in intermediate doping. While you see the cuprates are antiferromagnetic insulator in low doping and metallic in high doping. Further, the oxygen 2p level. The oxygen 2p level is different in nickelates and cuprates. Like for example, in cuprates, the oxygen 2p is near to the Fermi level, while in nickelates, this oxygen 2p is quite far from the Fermi level. The other subtle difference here is the Fermi surface. So when we look at the cuprates, generally speaking, that they have the one pocket Fermi surface, while nickelates have the two pocket Fermi surface, or even multiple pocket Fermi surface also sometimes. So we will be focusing on these two aspects, that what are the roles of this oxygen 2p's, and can we recreate this oxygen to this Fermi surfaces? Okay, let's see. So for that, we need to look at the synthesis of this nickelate. So Harold Hwang groups given the two-step process, that is topotectic reduction and rare earth substitution. And they end up with reducing the peroxide form in a layered form, which has a particular stoichiometry. And this particular stoichiometry shows the superconductivity below 15 Kelvin. Okay, fine. So what is special about this process? And they name this process as called Jenga chemistry. That's as you know that Jenga is a game. Okay, so the game is like what you need to take up the blocks one by one, and you need to place it on topmost level in order to complete it. Fine. So we can think of peroxide form made up of this Jenga blocks. So there are two NiO2 layers which is separated by rare earth or oxygen. But here there is a subtle difference. There is an exception. The exception here is that the rare earths are not the simply rare earth of one kind. There are two types of rare earth 1 and rare earth 2. So these are the rare earth substitution, and then it is and this particular structure is a bit unstable. So we do the topotectic reduction. What we do in topotectic reduction, we remove this oxygen blocks from this Jenga, and we end up with this type of the layered structure. So we can think of this layered structure in crystalline form as uh, ma- uh, converted to be 2D. Why? Because there is very low interaction between two consecutive layers. So we can think that, okay, we can think that this particular crystalline structure can be constructed as nickel oxygen square plaquettes, and in this nickel oxygen square plaquettes there are the rare earths which is lying. Fine. So we consider this type of model. uh, Further, if we look at the relevant orbitals which are important in this type of 2D physics for the low energy, is nickel 3D x square minus y square, nickel 3D z square, oxygen 2p, iterant 5D z square, and rare earth 4f. Here comes the debate about rare earth 4f orbital. It is still not resolved, and there are in the community there are debate about whether this particular 4f orbitals is playing important role or not. So we consider very safely the four orbitals, that nickel 3D x square minus y square, 3D z square, 2px, 2py, and rare earth 5D z square. And we consider that nickel 3D z square, 3D x square minus y square, oxygen 2px in along the x-axis, oxygen 2py along y-axis, and they are overlapping with each other. Further, there is oxygen overlapping. Okay, what about the rare earth? The rare earth here, it's extended orbital, but the one thing to keep in mind that this rare earth is due to the symmetric aspect, they don't directly overlap with 3D x square minus y square. So what they use 3D z square. Although things to remember is 3D z square is low lying in energy, so it is an indirect overlapping. Like rare earth is overlapping with 3D z square, rare earth 5D z square is overlapping with this. Also there are extended orbits. So this extended orbit, what I means that they overlap with each other also, so they form a separate square lattices which is interconnected. Okay, fine, we consider this and we create our Hamiltonian with this four orbital: 3D x square minus square, 3D z square, 2px, 2py, 5D z square, and we have this dispersion matrix. And this dispersion matrix, solving this dispersion matrix, we have Fermi surface like this. Okay, so the first thing to in mind is that we need to recreate this two pocket Fermi surface. Okay, we get it, this two pocket Fermi surface. What else? We observe that oxygen 2p, which is low lying in energy, shows very less contribution, even though there is contribution, but which is not so much dominating compared to other orbitals. Further, the nickel 5D z square remains almost dispersionless. So although this oxygen 2p and nickel 5D z square, 3D z square, this both are inert and doesn't play a dominant role in this, but still act as a mediator. It acts as a mediator for the super exchange, forming Lieb-like lattice. So we can effectively say that this type of 2D Fermi surface can be constructed from the this type of two half field, less than half field, and more than half field square lattices. Okay, so what could be the minimalistic model for nickelates? So we propose that there we can consider that there are two square lattices. So one square lattice is equivalent square lattice of NiO2, and one another square lattice, equivalent square lattice of rare earth, and there is a hybridization, say Vk, between both of them. And here T and T prime are the hopping parameter between these square lattices, within the square lattices. So we have to consider this also, that T and T prime are not this straightforward hopping parameter. They are renormalized, keeping in mind that there are other orbitals which is also contributing in the this type of super exchange process. Fine. And solving this, again, we have the two recreates this two pocket Fermi surface, And uh, tuning this vk, we can have different shape, but here I shown just vk as a scalar and t equal to t prime. Fine. So this is like we are reducing the complexity of the models, that we have crystalline form, then we say that okay, these are not orbitals which is relevant, and we reduce this complexity and we end up with some type of minimalistic model. So here I end my first part. So we can have this type of 5 orbital 2D physics model or 2 orbital 2D physics model with keeping in mind that here the parameters we can tune according to some real ab initio DFT calculation. And so for example, in effective 2 orbital model, we can tune T and T prime and V and VK, and hence we can reproduce this type of thing. Okay. So till now I talk about the okay, what could be the effective models, but you had to keep in mind that whenever we look at this synthesis process, there are two steps. So one is reduction and one is doping. Okay, fine. So both we can think of that either adding the elements, adding the element or removing element. Okay, these are the impurities in the sense. And what are this role of impurity? And answer to this question was given by a very famous scientist, Jacques Friedel, in late 90s, in early mid 90s. And he considered there is a spherical symmetrical impurities in a free electron gas, and he observes that there occurs the redistribution of energy, and this redistribution of energy are oscillatory in pattern, and this oscillatory in pattern decay radially. Okay, so we use this type of intuition in our model. So for example, we take a single impurity one orbital model. So we have Hamiltonian with conduction part and impurity, and the coupling between impurity and the conduction part. And we have the site dependence, apical or interstitial impurity. And using the T matrix approach, as Andreas mentioned, we can have the T matrix approach, which gives the Friedel oscillation. So from this T matrix, we can compute explicitly this change in spectral function as well as change in occupancy. And we look at this change in occupancy, and we find that there is oscillatory motion. Fine. The oscillatory motion is here. So here we also need to consider the three important length scale. The three important length scale are thermal correlation length, Friedel wavelength, and the impurity cloud length scale. Okay, so thermal correlation wavelength is the wavelength, we can say that, from where the thermal agitation dominates this Friedel oscillations. Okay, so they are like away from the impurity, extremely away from the impurity, and where we cannot find any pattern. The other thing is Friedel wavelength, as name suggests itself, is a wavelength for the Friedel oscillation. And the other length scale is RIMP, that is impurity cloud length scale. So we can say that this impurity cloud length scale is the length scale below which the two impurity can interact with each other. Okay, fine. So we see this type of pattern in two different type. Solving this one orbital model, we see that this type of pattern. So here I put the impurity at apical side and here at interstitial side, and you see there is a pattern which is different between apical and interstitial side, but away from the impurity it is showing the same Friedel oscillation. In animation you can see this very clearly. You see there is a particular different behavior of this oscillation near the impurity, and away from the impurity it's completely spherical. Fine. We solve this for multi-orbital model considering this 4 orbitals, this nickel 3D x square minus y square 2p x 2py and 3d z square. And considering there are two impurities, one is apical and one is interstitial. Apical mimics oxygen, 2p removal, that is reduction of this or addition of the oxygen, and rare earth impurities here, like in between the interstitial side. And we look at this pattern, and we again get this type of clouds. So you see that near the impurity, the cloud is different, but away from the impurity, I think it, okay. So it is not so much visible, but here you can see in animation, away from the impurity, it shows the very regularized Friedel oscillation. So from this, we can get the idea about the length scale of impurity cloud. And from this length scale, we can have the idea about what should be the nearest distance between two impurity to interact. Fine. So the summary of part 2 is Friedel oscillation are viable way to understand that what impurities brings into the this type of materials. Also, we can get the idea about its hybridization strength, its symmetry of the impurities, and other details of impurities. Further, from this, based on hybridization strength and RM, we can determine this length scale. As I mentioned, that at which length scale this two impurity will interact. And from that, we can roughly get an idea about finite proportionate regime at distance r, which is less than Rm from impurity, where the impurity clouds will overlap. And we might expect some different behavior or interesting state to study this type of nickelate structure. So thank you for attention. And I'm, yeah, I'm open.
Thank you, Alpesh, for this talk. Are
Yeah.
there any questions?
Yeah.
Peter?